Hello everyone. In today's session, we'll discuss about some basic applications of op-amps. So, op-amp is called as operational amplifiers. In the last session, we discussed about the introduction to the op-amp. In that, we discussed about the op-amp is having two input and one output. It is inverting input and non-inverting input and one output. And we discussed about the block diagram. And then we discussed about some op-amp input modes, and then we discussed about the op-amp parameters and all. And as I mentioned, the op-amps are used in many of the applications. Like it is used in active filters, like low pass filter, high pass filter. Then it is used in rectifier circuits, and we'll call it as a precision rectifiers. And it is used in comparator circuits, and many of the applications are using the op-amp. In today's session, we'll discuss some basic applications and some basic op-amp circuits. So we'll discuss about inverting amplifier, non-inverting amplifier circuits, and voltage follow circuit. So basic op-amp circuits. So before discussing about inverting amplifier and non-inverting amplifier, so we'll consider two assumptions. While analyzing any op-amp circuits, you should consider these two assumptions. One is zero input current. As we know, the input impedance or input resistance of an ideal op-amp is infinite. Therefore, the no current flows into an op-amp. This makes the input current to zero. The current entering into an op-amp is always zero. Because of large input impedance, the current which is entering into the op-amp will be zero. And the second assumption is it's called as a virtual ground. The important concept here. As we know that the ideal op-amp is having an infinite gain. The gain of an ideal op-amp is very high, or it is infinite. So we know that the output voltage V0 is equal to A into V2 minus V1, where V2 and V1 is the voltage at the non-inverting terminal and inverting terminal. So the V2 minus V1 is equal to V0 by A. The gain A is infinite. That means the difference V2 minus V1 is equal to 0. Right? V0 divided by infinite means it is 0. So therefore, V1 is equal to V2. This means that input terminals of an op-amp are always at the same potential. Thus, if one terminal is connected to ground, other can be treated as an virtually grounded. Physically, it is not connected to a ground in the circuit, but because of very high input, very high voltage gain, and the voltage at the inverting terminal and non-inverting terminal is the same. So this concept is called as virtual ground. So next we will discuss about inverting amplifier. There are two types of amplifiers. So there is one is inverting amplifier, the other one is non-inverting amplifier. We have operation of an op-amp. In that, if I'll give a signal to the inverting input and I'll connect non-inverting terminal to a ground, we'll get the output as inverted. So there will be a 180-degree phase shift between input and output. And if I'll give a signal to the non-inverting input, making inverting terminal as ground, then we'll get output as non-inverted. There is a 0-degree phase shift between input and output. So now we will discuss about the inverting amplifier, and we'll discuss about circuit diagram. Then we'll derive the expression for a gain. So in our amplifier, we are using negative feedback concept. So therefore, the feedback is always provided to the negative terminal of an op-amp. It is inverting terminal of an op-amp. And the advantage of using a negative feedback is it will stabilize the gain, and at the same time the bandwidth is improved, and your input impedance and output impedance, everything will be improved, and it will reduce the distortion in the circuit. That is the advantage of negative feedback. So in this case, the feedback is provided to resistance, the resistance that is called the feedback resistance, that is connected from output to the input. The feedback means the part of output is fed back to the input. Now, what is an inverting amplifier? An amplifier which produces a phase shift of 180 degree between input and output is called as inverting amplifier. There is a 180 degree phase shift between input and output, but the amplitude of input and output will be different. So I'll take a small input. For example, Vin is 1 volt and V0 will be more than that. It will be decided by the resistance RF and R1. The figure shows the inverting amplifier using op-amp. Here the input voltage Vin is given to the inverting terminal of an op-amp, and non-inverting terminal is connected to ground. The input is provided through a resistance R1, so it is called as input resistance, and the feedback is provided through a resistance RF, which is connected from inverting terminal to the output, and the non-inverting terminal is connected to ground. Non-terminal is connected to ground. So I named the potential, the point A as the inverting input and the point B as non-inverting input. Now from the circuit diagram, the potential at node B, the two nodes I mentioned, one is A, other one is B. From the circuit, the potential at node B is, because it is connected to ground, so potential at node B is 0. So therefore VB I will consider it as 0. VB is equal to 0. Now from the concept of virtual ground, that is the two input terminals are at same potential, therefore the potential at node A is also equal to 0, because the potential at non-inverting terminal, that is at node B, it is 0. If I consider VA is equal to VB is equal to 0. This is called as a virtual ground concept. Now from the circuit, here I consider the current through resistance I1 and current through resistance RF is IF. So input current, and another one we call it as feedback current. Now from the circuit diagram, I1 is equal to Vin minus VA divided by R1. It is the potential difference. Vin minus VA divided by R1 gives you current I1. Now what is VA? The VA is equal to 0. I substitute that, so I'll get Vin minus 0 divided by R1. Therefore I1 is equal to Vin divided by R1. Similarly, the feedback current IF is equal to VA minus V0 divided by RF. The potential inverting terminal and potential at the output, that is VA minus V0 divided by that resistance, that is RF. So VA is 0, so 0 minus V0 divided by RF. So therefore I'll get IF is equal to minus V0 divided by RF. Since the op-amp input current is 0, no current is entering to op-amp because of large input resistance. I1 passes through RF. I1 passes through RF as IF. Therefore, if I apply a Kirchhoff's current law to a node A, the current entering to node A is I1 and the current entering to a node, current leaving the node is IF. Therefore, I1 is equal to IF. What is the equation for I1? I1 is V in by R1 and IF is minus V0 by RF. So therefore V0 is equal to minus Rf by R1 into Vin. So here Rf by R1 is called the gain of an amplifier, and the negative sign indicates that the output is inverted. The negative sign indicates that the output is inverted. And I have taken the input and output waveform of an inverting amplifier. I have taken one sine wave, the one cycle sine wave, and they can observe there is a output. There is a 180-degree phase shift between input and output. So when input is maximum, the output is minimum. When input is minimum, the output is maximum. That is called as there is a 180-degree phase shift between the input and output. So this is a derivation for a inverting amplifier where V0 is equal to minus Rf by R1 into Vin, and this Rf by R1 is called as a closed loop gain. Closed loop gain, that is indicated by, or it is denoted by ACL, closed loop gain. It is given by Rf by R1. So if Rf and R1 is equal, then V0 is equal to minus Vin. So there is no change with respect to the amplification factor. The amplification factor is 1 here. So only there is the output and input is inverted. It's about inverting amplifier. The next circuit we will discuss about non-inverting amplifier. As the name itself indicates that here the input is given to the non-inverting terminal of an op-amp. So non-inverting terminal of an op-amp, we have provided the input signal. And here an amplifier which amplifies the input without producing any phase shift between input and output is called non-inverting amplifier. So there is no phase shift between input and output. So the phase shift between input and output is 0. This is called as a non-inverting amplifier. And the figure shows a non-inverting amplifier using op-amp. And here also negative feedback is provided. As I mentioned, the feedback is provided through resistance RF. And it is connected from output to a inverting terminal of an op-amp. And I used one more resistance that is connected to the inverting terminal, and other terminal of an op-amp, other terminal of resistance is connected to ground. This is about the circuit diagram. From the circuit, the potential at node B. What is the potential at node B? It is equal to Vin, because here the input is given to the non-inverting terminal. Now from the concept of virtual ground, the two input terminals are at same potential. Therefore, the potential at node A is also same as the potential at node B. Therefore, VA is equal to VB, that is equal to V. Now from the circuit diagram, the direction of the current is shown over there. This is I1 and IF. Now based on the direction of the current, we will write the equation VA minus V0 divided by R1. Potential at A, potential at the terminal node A, potential other terminal, that is VA minus 0 divided by R1. What is VA? VA is Vin. So write it as Vin minus 0 divided by R1. So I got the equation Vin by R1. I1 is equal to Vin by R1. Now the feedback current IF is equal to V0 minus VA by RF. V0 minus VA divided by RF, and written as V0 minus Vin by RF. Therefore, IF is equal to V0 minus Vin divided by RF. So I got the equation for input current and the feedback current. And again, there is no current entering into the op-amp. The current which is entering into the op-amp is 0. Therefore, the current, your input current and feedback currents are same. If I apply a KCL, the Kirchhoff's current law to node A, then I1 is equal to IF. Since op-amp input current is 0, IF passes through R1 as I1. Therefore, we'll write it as I1 is equal to IF. Now, what is I1? I1 is V in by R1 and IF is V0 minus V in by RF. Further, we'll simplify it. So, V in by R1 is equal to V0 by RF minus V in by RF. Now, I'll collect input and output terms separately. So, I'll take output term to the LHS and input term to the RHS, right hand side. So, V0 by RF is equal to V in by R1 plus V in by RF. And V0 by RF is equal to 1 by R1 plus 1 by RF into V in. For the simplification, you get RF plus R1 divided by R1 into RF into V in. We'll take RF to the other side, then RF it cancels. So we'll get the answer as V0 is equal to 1 plus RF by R1 into V in. So output voltage is given by 1 plus RF by R1 into V in. And here 1 plus RF by R1 is called as the gain of an non-inverting amplifier. And here the positive sign indicates that there is no phase shift between input and output. As I mentioned, the phase shift in a non-inverting amplifier is 0. The figure shows the input and output waveforms of an non-inverting amplifier. The input here considered a sine wave, and the output is also the same. There is no phase shift input and output. And again, here the gain will be decided by resistance RF and R1. So it's a very important circuit. Exam point of view also we will decide, we will ask inverting amplifier or non-inverting amplifier, and they will give a problem to find the output voltage or find the gain of an inverting amplifier or non-inverting amplifier with the following specification, like you R1 RF and you have to find out V0 and you have to find out the gain. And in some of the problem they ask design inverting amplifier and non-inverting amplifier. Design the circuit, inverting amplifier, non-inverting amplifier. At that time you have to find out the resistance values, R1 and RF values you have to find out. And as it is used for an amplification purpose, the output voltage is always greater than the input voltage. So this is about the op-amp as inverting amplifier and non-inverting amplifiers. So in the next circuit we will discuss about now we'll discuss about the op-amp applications. The different circuits we'll discuss. This one is voltage follower. Then we'll discuss about summing amplifier, also called as adder circuits. Again, we'll consider 2 input voltages. Later you can consider 3 input voltages. Then we'll write the output. The output will be the addition of the input voltage connected in the terminals. Then we'll discuss about op-amp as an integrator. And the output and input is related by an integral equation there. The output is the integral of input voltage, so it's called as an integrator. Then one more application we'll discuss op-amp as a differentiator. So output will be the differentiation of input voltage. And the last circuit we'll discuss about comparator. The comparator means it will compare the 2 voltages given to the inverting terminal and non-inverting terminal. Based on your sine wave will be converted to a rectangular wave or a square wave. These are all the applications we'll discuss. Then we'll discuss some problems related to this on op-amp parameters, then op-amp applications and all. The first application of an op-amp is voltage follower. As the name itself indicates, the voltage follower means here output follows the input. Output and input voltages are equal in magnitude. The circuit in which the output voltage follows the input voltage is called voltage follower. The figure shows the voltage follower circuit using op-amp, and the circuit diagram is here. The signal, the input signal is given to the non-inverting terminal of an op-amp, and the inverting terminal is directly connected to ground. So the feedback is provided, it is directly connected to ground, it is shorted. Whereas in the previous circuit, inverting amplifier, non-inverting amplifier, I used one feedback resistance from inverting terminal to a output, whereas here it is directly connected. So this is about the circuit diagram of a voltage follower. Now from the circuit, the potential at node B is equal to Vin, and as I mentioned, I given a signal to the non-inverting terminal, that is Vin. Therefore, the potential at node B is Vin. We'll use the concept of virtual ground. The two input terminals are at same potential, therefore the potential at node A is same as the potential at node B. That is VA is equal to VB is equal to VN. The node A is directly connected to output, hence V0 is equal to V. V0 is equal to V. Now since VA is equal to Vin, in a voltage follower, the gain is unity. A voltage follower is also called as a source follower or unity gain amplifier, or it is also a buffer amplifier, or it is an isolation amplifier. Source follower is also called as unit gain amplifier, buffer amplifier, or isolation amplifier, and the figure shows the input and output waveforms of an voltage follower. Here you can observe the input voltage given, and the output voltage is same as input voltage. Therefore, the gain of the voltage follower is 1. Output follows the input, therefore it is 1. So this is some of the application of an op-amp, and it is used as an unity gain amplifiers, and it is also used as a buffer amplifier also. Now to summarize this concept, and so we discussed about the basic op-amp circuit, and first we consider there are two assumptions. There you go. The assumptions, the two assumptions. One is because of large input impedance, the current entering into the op-amp is 0. Therefore, current entering into the op-amp is 0. And one more assumption is your virtual ground. The virtual ground concept is as a potential at inverting terminal and non-inverting terminal same, and if non-inverting terminal is connected to ground, then inverting terminal is also connected to ground. So that concept is called as virtual ground. In physical, there is no connection between, the ground is not connected to ground. So because of the potential at inverting terminal and non-inverting terminal are same, that concept we will call it as virtual ground. And we discussed about inverting amplifier. So inverting amplifier, here there is a 180-degree phase shift between input and output, and the output is inverted, and there is 180-degree phase between input and output. And here in the circuit we used feedback, and we'll call the feedback as a negative feedback, and it is part of output is connected to the input through a resistance RF, and we get the output V0 is equal to the negative of RF by R1 into Vin. And RF and R1 will decide the gain factor here. The gain of an amplifier is given by RF by R1, and the negative sign indicates that output is the inverted version of input. The next we discussed about non-inverting amplifier. Non-inverting amplifier, here there is no phase shift between input and output. The output and input is not inverted, and here the input signal is provided to a non-inverting terminal, and the inverting terminal is connected to a resistance R1. Again, now negative feedback is provided through a resistance RF. Therefore, here the output voltage V0, it is 1 plus RF by R1 into Vin, and the gain of the amplifier is given by 1 plus RF by R1, and as the positive sign indicates that the output is non-inverted. Then we discussed about the op-amp application, and that we discussed about voltage follower circuit. The voltage follower, as the name itself indicates, here the output follows the input, so V0 is equal to Vin. Here the signal is given to the non-inverting input, and the inverting input directly connected to output shorted. Therefore, the gain of an amplifier is 1, and it will provide a unity gain, and it is also used as a buffer circuit. This is about one of the application of the application. In the next session, we'll discuss about the op-amp as an adder circuit. And then we'll discuss about op-amp as an integrator, op-amp as an differentiator, and op-amp as a comparator. Now, then we'll discuss few problems on that. Few problems on inverting amplifier, non-inverting amplifier, then op-amp as an adder circuit, and the differentiator and integrator. Op-amp as an adder is also called as a summing amplifier. Summing amplifier means here we give more than one input voltages, either to the inverting input or non-inverting input. So I will consider the input will be given to the inverting input as V1, V2, V3, and then output will be the addition of all those things. If I will connect the input to the inverting input, then output will be inverted again. If I will give an input to the non-inverting input, output will be non-inverted. There is no relation between input and output. In integrator also, integrator, there is one more element in the circuit, it is capacitor and one resistance, and here the output voltage will be the integration of input voltage, and even the differentiator circuit also, the output will be the differentiation of input voltage. Op-amp as a differentiator circuit and the integrator circuit. And the major application of an op-amp is as filter circuits, low pass filter, high pass filter, band pass filter, then band reject filters and all. And it is used as instrumentation amplifier. It is used as in rectifier circuits, and the op-amps are used in oscillator circuits. Oscillators, to provide an oscillation in the circuit, we use op-amps. like RC phase shift oscillator, then Wien bridge oscillators, and all the applications of an op-amp. And the commonly used op-amp is practical op-amp is mu-A741. Its number is mu-A741, and it is a 8-pin IC, and it requires dual supply and the two input, inverting input and non-inverting input, and commonly used. Okay, thank you.